Okay, so in 7.6, we're shifting our attention to exponential functions and the graphs of exponential functions. So we have already graphed lines, right? And those are linear functions. And lines have slopes and they have y-intercepts, and they can be parallel, perpendicular, they can be undefined slope, they can be a slope of 0. We know a whole lot about lines. We don't know a whole lot about exponential functions, okay? So we're going to start by talking about the definition for it and then look at some on the graph and then try and dive a little deeper, okay? So an exponential function is a function that's written in this form. Y equals a times b all raised to the exponent of the x. A couple of things that we have to remember here in this particular case, okay? A is not allowed to be 0. Can someone tell me why a is not allowed to be 0? Yeah, if it was 0, then it would wipe everything out and we'd have nothing to work with there. Okay, so a can't be 0, all right? B has to be greater than 0, meaning it has to be a positive number, okay? And b cannot be a 1. Someone tell me why b cannot be a 1. Because what's 1 to anything? You get 1. 1 to the 50th is still 1, comes linear, okay? So if we have these constraints going on, then that's our definition of an exponential function. Okay, so let's get a better understanding by taking a look at a very simple one. Yeah. It has to be greater than 0. It says right there. So let's take an example of y equals 3 to the x. Okay, what we're going to do is we're going to graph this and our graphing calculator and take a look at it. So go ahead and take calculators out. We'll go to the y equals button here. Clear everything out if there's anything that's already in there. And let's take a look at y equals 3 to x. So before we go though, what's the value of a in this case? So here, I'll move this out of the way. What would be the value of a in this case? How does it match up to this? The value of a is 1. Very good, Brandon. Most people say the value of a is 3. But that's not what a is, right? A is the value of 1. What's the value of b in this case? 3. So b in this case is 3. That's our base. So we have a base of 3 and we have an exponent of x. The value of a is in 1 in this case. So it's the regular parent graph. So here to graph that, we go y equals 3 and then we put a little caret button there and then we say x. So 3 to the x. Looks like this. Okay? And then go ahead, everybody hit zoom 6. Take a look at it and tell me what you think it looks like. You do that and talk to your neighbor and I'll set it up over here in Fluid Math as well. Talk about it. Okay, so you guys should have this graph kind of in your graphing calculator as well, right? Yes. How would you describe it? It is a function. It's not linear. It's an exponential function, okay? But it is a function, okay? What I've given you a couple of I've given like a screenshot kind of what this should look like because I want to point some things out, all right? You'll notice that it looks like right here it kind of flattens out, right? So every exponential function has what's known as an asymptote, which is basically a line that the function gets close to and behaves more like for big and small values of x. It can't actually cross it, so I don't want to tell you that it's a line that it can't cross, but it does get very, very close to it. But here's the important part about what it means to be exponential, okay? I can put the table in here. So at 0, we're up here at 1. Okay, so at 0, I'm up here at 1. At 1, I'm up here at 3. So if I draw these little bars here, okay, I want to point out what it means to be exponential. What it means to be exponential. At 2, I'm up here at 9. Everybody agree with that part? Okay, so what I'm about to say is how you can tell if a function is exponential. What you have to test for is this. You have to test for equal distance. For equal distance, you want equal factors. So in this one, it's times 3, and times 3. So for every unit value that I increase x by 1, I increase y by a factor of 3. That's what it means to be exponential. You have equal distance for equal factors. That's not linear, right? Linear is slope, right? Rise for run, the ratio. This ratio is factors to run. So every time I increase by a factor of 1, my output is increased by a factor of 3 And that's why 3 is the base. Does that make sense for you? That's what it means to be exponential. So now notice that when we get on the left-hand side, when x becomes negative, notice that these decrease, right? But they're still by the factor of 3. But notice that, how do I write, what does 3 to the negative 1 mean? It means by a factor of a third. What's 3 to the negative 2 mean? It means by a factor of, I only get a 1/9 output there. So it does work for you when you're over here in the negative exponent as well. And you can see that if I zoom in, right, a whole bunch, if I keep zooming into this thing, so you'll notice that each of these spans are still the same equal factor no matter where we go. Okay? So I can zoom back out. That's what it means to be exponential. Equal spacing for equal factors. Okay? So if I gave you this one, if I gave you y is equal to 5 to the x, what would my factor be, my growth factor? Maybe 5, right? So I'd have 1, or have 0, comma 1. I'd have 1, comma 5. I'd have 2, comma what? What would be on that graph? 25. I'd have 3, comma 125. See how that works? So I'm growing by different factors there, okay? Okay, so what I've given you here is I've given you a generic a times b to the x. This is a generic exponential function, okay? The value of a is 3, so I'm going to actually set the value of a back to 1 because that's going to be our general function, okay? And then I have b is actually set to 2, so this is the function y equals 2 to the x, okay? So what happens to the graph when I take a and I make it a negative 1, a negative value? What do we see? It's the opposite of that, right? It reflects it over the x-axis, right? So if my a value is negative, I'm reflected over the x-axis. So if I was going to ask you a question, what is negative 2 to the x? If I was going to graph that one, what would it look like? It would actually be the exact same graph that I have on the page right here, right now. See that? It's the exact same one, okay? What if I said that it was negative 3 to the x? It would still be reflected, but the points would be a little bit different, right? I'll be rising by a factor of 3 instead of rising by a factor of 2, okay? So let's get rid of this one right now. So we know that the a value is going to flip my graph, make it positive or negative, but it also kind of increases the stretching factor, right? Okay? What if b is, let's make this really non-discrete here. Let's make this like that, okay? Here we go. So if my b value is between, look at that. Did you guys see what just happened there? Okay. So yeah, it no longer came, it went from being an exponential growth, which is this one, to an exponential decay, which is that one. So what are my values of b that make this thing an exponential decay? What numbers are they between right now? It's between 0 and 1, right? What if I go past 1, right? Notice I'm at 1.37. I have exponential growth. If I go between 0 and 1, like 0.76, what do I have? I have exponential decay. What do you think would happen if my b was negative? Is that even possible?
Negative exponential growth or negative?
Look at this. What do I get? If my b is negative, what happens over here?
It can't connect.
Yeah, okay. So if my b value is between 0 and 1, I have exponential decay. If my b value is greater than 1, I have exponential growth. If my a value is negative, I have the reflection of either exponential growth or exponential decay. Does that make sense? Okay. So we're getting all these things down here, right? So, okay, if I give you this, y is equal to negative 3 times 1.2 to the x. Okay. Are you able to visualize what this graph is going to do? Will it be exponential growth or exponential decay? Well, okay, I should have asked the question. Will the graph be reflected over the x-axis or not reflected over the x-axis? It will be reflected, right? What's the value of a in this case? Negative 3. What's the value of b in this case? 1.2. So the graph, like, can you trace it out in the air, what the graph should look like? Trace it out in the air, what it's going to look like. Is this what you guys came up with?
Yeah, completely.
Oh, wait, sorry. My x value didn't work out.
There.
Whoa, that's not an x, that's a question mark. Let's try it again. There you go. Is that what you guys came up with? Is that what you came up with? Oh, sorry. Okay. Why is it doing that? What makes it do this?
It's the negative A.
Okay. So if I make that a positive, then I would get growth, right? Okay. Now if I take that out and make it a 0.2, what would I get?
Huge line.
That do I even where'd that thing go? Let's get rid of that. Where'd it go?
Zoom in. Keep zooming.
There we go. There it is. Okay. Okay. Okay, right now, what do you think? Exponential or not? Yes or no? Okay, let's talk about why you think it's exponential. What's the definition of exponential again that we're referring to? Yeah, for equal units, we get equal factors. So, what's my factor here? So here's my equal units, right? From 0 to 1, 1 to 2, 2 to 3. What are my factors here? What's my ratio? The ratio is 3, right? So that's a 3, 3, and a 3. Okay, if I were to graph these points, if I were to quickly graph these points, I'd have 0, negative 1, 1, negative 3, 2, way down here at negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would have this graph here. Okay? Do you think you could come up with the equation for that graph? What would it be? Negative 3 to the x. And that would give us that graph right there, right? The value of a would be negative 1. The value of b would be 3. Does that make sense? So far, so good? Okay, so that's... Alright, so the setup is this. They say there's 30 flower beetles left alone at the start. The beetle population doubles each week. How many would there be in 56 days? So notice that we have written something that's doubling in each week, okay? So how do you write something that doubles in each week? Well, that's the given by the function here. So we're taking our initial amount, we're taking our base, and we need an exponent in order to double things. So if I'm going to double things twice, that'd be 2 squared, and then times our initial amount. I'm going to double things 3 times, that's 2 times 2 times 2. That's where exponential functions come into play. So I have 30 times 2 to the x. Now that's x is in number of weeks. So if I have 56 days, how many weeks would that be if it's 56 days? 8. 8 weeks, right? Okay, yeah. No, that's 16. Yeah. Good. So I have this. So now I want this, all right? So if this is in weeks, I want f of 8 is equal to 30 times 2 to the 8th, and this is a simple plug and chug. Now 2 to the 8th we know, right? Didn't we do that one earlier today?
I think so.
We did. 256. Reverse them. You're close. Okay, so that's 30 times 256, which is telling me 7,680. So you guys got? Did you actually do it? Or did you just wait for me to do it?
I did it.
7,680.
No, that's
Is that wrong?
wrong. No, I multiplied by 70. I'm sorry.
Okay. All right, we're going to graph this exponential function y equals 3 times 2 to the x, okay? For the homework, you will have to do some graphing, and this is how I'd like you to do it, all right? Right away, what's the value of a? 3. What's the value of b? 2. So we're going to have 3 times 2 to the x here. So we need to identify your values of a, b, and c. So here's how I want you to set the table up. So we'll take the table of values of x, okay? We'll say y is equal to 3 times 2 to the x, and then we'll come up with our ordered pair x and y. Just for a couple of points here to get an idea of what's going on. So let's do negative 1, 0, 1, and 2. Okay? Negative 1, 0, 1, 2. We'll do those all by hand, and then we'll use a calculator to make sure we're doing it right. So if I plug in a negative 1, what's 2 to the negative first? That's 1 half. What's 1 half times 3? 3 halves. Yeah, very good. So 3 halves, okay? So what point would I put on here? Negative 1, comma, 3 halves. Very good, okay? Now, what if I plug in a 0? What's 2 to the 0? 1. What's 3 times 1?
3.
So I know the point that 0, comma 3 is on the graph. Plug in 1. What's 2 to the first? 2. 2 times 3 is 6. So the point would be 1, comma 6. You guys heard that part? Do 2 one more. 2 squared is 4. 4 times 3 is 12. So then the point 2, comma 12 would be on the graph. Okay, so now that I have all that information, I actually want to do a pretty decent job of graphing this out. So I would take a straight edge, and I would do the best I can to graph this out. I know. So negative 1, so I'll count these as, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I'm going to use equal units here. 1, 2, 3, 0, 1, 2. That's all I have. So negative 1, I would be at 3 halves. So that's up 1 1/2. Okay. At 0, I'd be up at 3. 1, 2, 3. At 1, I'd be up at 6. 1, 2, 3, 4, 5, and 6. And then at 2, I would be up here at 12. So here's 12. Okay. So check to see if this is making sense. Am I getting equal growth factors for equal distance? Yes or no? Yeah, I am, right? I'm getting equal growth factors for equal distance. So this would represent a good sketch for exponential. Okay? And then you can also use your graphing calculator to make sure that you're doing this correctly. So you go into the graphing calculator and you would say this. If I want 3, and then I would use parentheses 2, and then close parentheses caret x. So this guarantees that the x is only affected by the base of 2 and not 3. Alright? Then I'd hit zoom 6, so we're all looking at the same thing. And I'd look to see to make sure that what's on the calculator is pretty close to what's on the screen, or on my homework. Then I would also take advantage of the table. So I'd go second table and look, okay? At negative 1, I should be at 1.5, and we were. There's mine right there. If I was at 0, I'm at 3. If I am at 1, I'm at 6. And if I'm at 2, I'm at 12. So it looks like my graph is absolutely perfect, matching with what we did as a sketch. So this is what you would do to sketch it on the homework tonight. So here's a different type of a problem. They're saying, what is the solution or solutions of 2 to the x equals 0.5x plus 2? And the way that they solve this is they actually solve it using the calculator. So that's kind of fun. So I'm going to show you how to solve this using the calculator. So let's pull this up right here. Okay, go to your y equals button and clear out anything that's already in there. Okay. So what we're going to do is we're going to graph 2 different equations. We're going to graph the equation on the left and the equation on the right, and we're going to see where they cross. That's what we're going to do. That's our game plan. So we're going to go 2 caret to the x. This is going to be my first equation. That's my exponential equation. Then I'm going to go down and punch in a second equation, which is the one on the right-hand side. So I'm going to say 0.5x plus 2. Okay? So notice I'm graphing 2 separate equations in 2 separate y equals. And I'm interested in where they cross because that's where they're going to be equal to each other. So then I'm going to hit zoom 6 to make sure that we're all staring at the same picture. So the first graph in the blue graph is my exponential graph. And then this other graph here, this red graph that's coming into the window right now, that is my linear graph, and that's the one on the right-hand side. So does it look to you like they cross? It sure does, right? And it looks like they cross in 2 different places. Looks like they cross here and there. Okay? So we need to adjust maybe the window to see, or we could just go ahead and try and use the window that we have and find the intersection points. So let's just go ahead and try and find the intersection points. So we're going to hit second, and we're going to hit the trace button, and we're going to calculate where these 2 lines intersect, which is option number 5. That's what we're looking for right now. So I'm going to push enter, and that's asking me, is my little butterfly on the first curve? And we'd say yes, it's on the first curve. So I push enter. Huh? No, because it actually, it calculates for you.
Why does it ask?
It asks me for the second curve right now. That's because I have 2 different lines here, right?
I mean, like what? Like, does the when it's
Oh, it just, you could have like 5 different curves in there, and if you only want the intersection of 2, it wants to know which curve you want. That's why it does that. Okay, and then do you want to guess? No, I don't really want to guess. Just tell me what the answer is for this one. Okay, it gave me this one. It gave me 1.44 and then the 2.72, and that counts for one of them. They have that as well. 1.44 and 2.72. Okay, now to get the other one, right? I want to do this again. I'm going to go second trace. I'm going to calculate option number 5. But I'm going to move a little closer to the other point. So I'm going to take this butterfly and I'm going to move it over here and go to the left of my point. And then push enter. And then second curve. It already jumped to the second curve. Push enter again. I don't want to guess. And there, now it gives me that second point. So whichever one it's closer to, if there's 2 intersections, it will tell you. So they may ask you to use your calculator to find the intersection of 2 points. So we can do that as well.